Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, I'm going to be covering coffee cup So we learned about calorimetry in a previous video where we were calculating the internal energy at constant volume. Well, another type of calorimetry process that we can do is what we're dealing with when we're at constant pressure. And this would really be when we're calculating the enthalpy of a reaction that's occurring. Rather than using that bomb calorimeter that we saw previously, we're now going to be using a coffee cup calorimeter, which has some of the same premises, but is a slightly different setup. In a coffee cup calorimeter, you literally can have two coffee cups, and there's a loosely fitted lid that's placed on top. Now, much like the bomb calorimeters, a thermometer is placed inside of the solution or inside the surrounding area that's surrounding the actual reaction itself. And we monitor how that solution changes in temperature. If we know what's happening to the solution, which in this case represents our surroundings, we can then infer what's happening in the reaction. The reaction would be equal but opposite to the system itself. Now, much like before, we would calculate one and then make the other opposite, and then we can infer information further down. Now, the big difference for how we're going to go about solving the heat of the surroundings, in this case, the solution, is a slightly different calculation than what we did with the bomb calorimeters. We now are going to be using that our old heat equation, which involves the mass and the specific heat of the solution. So we need to take into account how much is present in order to solve this. Because we're measuring at constant pressure, we know those other variables drop out. So the enthalpy of the reaction is directly equal to just the heat of the reaction when we're doing this. A great way to remember which equation you use where, the bomb calorimeter, bomb has a shorter, only 4 letters compared to coffee cup calorimeter. So in the bomb calorimeter, you'll use that short heat equation, Q equals C cal times delta T. In the coffee cup calorimeter, you're going to use the longer heat equation, the mass times specific heat times delta T. Okay, so let's get started. So it says here, what is the enthalpy of the reaction of magnesium plus hydrochloric acid to produce magnesium chloride if 0.158 grams of magnesium reacts with 100 milliliters of solution and changes the temperature from 25.6 degrees Celsius to 32.8 grams, 32.8 degrees Celsius. And so some information we know we have 0.158 grams of this material. We have 100 milliliters of solution, and we have these changes in temperatures. And we're going to assume that we have the density of this substance is that of water, and also that the specific heat is that of water. Okay, so those should be provided in the problem for you. Now, since we're dealing with the coffee cup calorimeter, a constant pressure situation, we know we want to figure out the heat of the solution first. Again, the solution represents our surroundings. And to solve that, we're going to say, well, that's the mass of the solution times the specific heat of the solution times delta T. Now, be very careful on this problem. A lot of students will see this number and say, oh, that's a mass. I'm going to plug it in. But remember, a solution is a solute plus a solvent making that mixture. So therefore, what we want to put in is not the mass of the solute, the thing that's being dissolved. We need the overall mass of the solution. How we're going to figure that out is by the fact that we have 100 milliliters of it. And we know that the density is 1 gram per milliliter. So if we have a volume and a density, we can calculate the mass of the solution by taking our density times the volume, which would be 1 times 100. So that gives us 100 grams. Okay, so make sure you're putting the right grams here. That's where I see a lot of students, their downfall in this type of problem. The specific heat is going to be that of, for water, so 4.18 joules divided by grams times Celsius. And then the change in temperature is going to be your final 32.8 minus the initial 25.6. When we plug that all in, we end up with 100 times 4.18 times 32.8 minus 25.6. And that gives us 3,000 or 3.0, 3,009.6. And this is joules for the solution, the heat of the solution. So what that tells us, if that's the heat of the solution, the heat of the reaction would then be the same thing, but opposite. The reaction lost that heat. The solution gained that heat. And this also would equal the enthalpy of the reaction because, again, those other variables drop away. And so we're looking for our enthalpy in units of kilojoules per mole. And so this is where the mole, we need to figure out how many moles of the substance we have. And so we can take our 0.158 grams of magnesium, and we will first get that to moles by using magnesium's mass of 24.305 grams is to 1 mole. And so that would give us a total of 0.158 divided by 24.305. And that gets us 0.00650 moles of that substance. And so then to get our final answer in the proper units, the enthalpy of the reaction would be equal to our heat of reaction, but we want to convert that to kilojoules. So let's first convert this to kilojoules. So this would be negative 3.0096 kilojoules. I'm just dividing it by 1,000. So we have negative 3.0096 kilojoules, and we're going to divide it by that mole amount. And when we plug that in, we end up with negative 3.0096 divided by 0.0065, and that gives us negative 463 kilojoules per mole of magnesium. Okay, let's just, again, we would classify this as an exothermic process because heat would be exiting as this reaction has occurred. And last but not least, it says, what will be the final temperature of the solution in a coffee cup calorimeter if 50 milliliters of sample of 0.25 molar HCl is added to 50 milliliters sample of 0.25 molar, should say molar, NaOH. The initial temperature is 19.5 degrees Celsius, and the enthalpy for the reaction is negative 57.2 kilojoules per mole of sodium hydroxide. And we're to assume that the density of the solution is the same for water and same with the heat capacity. So what we would need to do in this case here is first work with our enthalpy of the reaction. And we need to get this just to the heat of the reaction first. So we got to get rid of that moles of sodium hydroxide. So how we can get rid of that moles of sodium hydroxide? Well, we have to first calculate how many moles are present. So we're told that we have 50 milliliters. So moles we know is equal to the molarity times volume. So we could take the molarity, which is 0.250, times the volume, which is 0.0500 liters. And that would give us 0.25 times 0.05, and that gets us 0.0125 moles of NaOH. And so to get rid of the moles here, we would just need to multiply by that value. So that would give us negative 57.2 times 0.0125, and that gets us negative 0.715 kilojoules. So that number would be equal to the heat of the reaction, because again, at constant pressure, that's all the enthalpy is equal to. What that also helps us to figure out, well, the heat of the solution would be equal to that same number, but opposite. Okay. And so now we can use the heat solution formula, the fact that the heat of the solution is equal to the mass of the solution times specific heat times delta T, and solve for our final temperature. Now we want to make sure when we plug in that we're plugging in the proper value. Notice that our heat of solutions is in kilojoules. However, our specific heat is in joules. So we'll want to convert this to joules before we plug it in. So that'd be 715 joules. So now we can say 715 joules is equal to, again, when we talk about this mass of solution, that's going to come from the fact that the solution volume is 100 milliliters. So we have 50 plus 50. And so that's going to give us a solution volume of 100 milliliters, which if the density is 1 gram per milliliter, that also means we have 100 grams of solution times the specific heat of water, joules divided by grams Celsius. And now our change in temperature would be the final temperature minus whatever it was initially, which was 19.50. It then becomes algebra. So we would take 100 times 4.18, and that gives us 418 times TF minus 19.5, and that's all equal to 715 joules. Because we're running out of space, I'm going to go ahead and erase this over here just to create some working room. So then we would then distribute. So let's just work over here. We would then say 715 joules is equal to 418 times TF minus, you take 418 times 19.5, and that gives us 8151. The TF, we would then take the 815 and 8151 and add it to both sides. So we have 715 plus 8151, and that gives us 8866. The final step, you take your TF and you'll divide both sides by 418. So 886 divided by 418, and that gets us 21.2 degrees Celsius as our final answer. So go ahead and check your math. Again, the steps here, we canceled out the moles of sodium hydroxide first, and then we were able to state what the heat of the reaction was. We made that value equal but opposite to represent the heat of the solution. We then plugged in the mass of solution, and that's based off of the fact that we have 100 milliliters of solution with a density of 1 gram per milliliter. And then we solve for our final temperature. I hope this video helped you understand how to do these coffee cup calorimeter calculations. Make sure you guys like, comment, and subscribe, and come back to see more videos in the future. Have a great day. Talk to you guys soon.